Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. We have been over last few lectures discussing the principles and postulates of quantum mechanics. So far we have discussed three postulates of quantum mechanics. The first postulate of quantum mechanics told us that for any quantum mechanical system there exists a state function that completely specifies or completely defines or describes the state of the system. That means everything you need to know about the system is out there in this state function or wave function. The second postulate told us that if you want to measure any classically observable quantity, for every classical observable in quantum mechanics there exists an operator. And in the third postulate it said that when you make a measurement corresponding to a quantum mechanical operator A, the only values that will ever be observed are actually the eigen values of operator A. So, in this context we learned how to determine eigen functions and eigen values of different operators, because the eigen values are the only quantities that are going to be observed in an experiment. The question now that we can ask is that if the system is an eigen function of the operator, then it is all right. When we make a measurement, we actually get the result as the eigen value. But what if the system or the state of the system is not an eigen function of the operator A? Because we have seen that for a given operator there are only a few functions that we can define as an eigen functions, but there will be a large number of functions that would not actually be the eigen function of this operator A. In that sense, in that case, what can we do? That means, if the system, if the state of the system is not an eigen function of the operator and I make a measurement corresponding to operator A, what will be the outcome? To answer this question, we actually require the help of another postulate, and this is what would be the theme of today's discussion. This brings us to the next postulate, that is postulate number 4, which says that if you have a system which is described by a state function, a wave function psi, which is normalized, if you have that system, then the average value of this observable, that corresponds to this operator A, is given by this relation, where the left hand side is the way we denote the average value, or also this is also called as expectation value. The left hand side of this expression is what is known as the average value or the expectation value. This quantity is also called as expectation value. Or average value. The right hand side shows how we can determine or obtain this expectation value. This is the relation that we have to remember in today's class. This is simply an integral where the psi star is the complex conjugate of the state function, psi is the state function, A is the operator that I am currently interested in. If I want to determine what is the average value or the expectation value of measurement when I measure observable A, the answer is that I must evaluate this integral. This expression holds the answer to the question that we asked, that if the system is not an eigen function of the operator A, then what would be the outcome of this measurement. Please remember, when we are telling about this expectation value or average value, we have one particular thing in our mind. In quantum mechanics, we know that when we do a measurement on a system, we get an outcome, and that outcome is an eigenvalue. How does this average value or the expectation value come into a picture? We often use average value when we have different measurements and different expectations or different outcomes, and at the end we might want to express the the conclusion of this experiment as some kind of an average. For example, when you have a test in your class, each of you get some marks, and to know how overall the class performed, one can calculate the average of the marks. So, this is simply something very similar. If we want to measure a classical observable, we make many measurements. In quantum mechanics, there lies a subtle difference between the two things. One is that we do not measure multiple times the same observable on the same system. Rather, what we do is that we prepare many copies of identically prepared system and make a one time measurement of that observable on each of these systems. So, when I do this, when I make one time single time a measurement of a classical observable on multiple copies of an identically prepared system, I get many outcomes, and the average or the expectation value of that entire set of experiment is given by this operator A. We would continue this discussion by considering two cases. Suppose I have my state function is given by x here, excuse me, the state function is given by psi here. In the first case, I see that let psi be an eigenfunction of operator A. So, I define, so this is my operator A, let me define that operator A has this eigenfunction f n with an eigenvalue of a n. We already know that if operator A is a Hermitian operator, then it always has a complete set of orthonormal eigenfunctions. So, this f n is one of these f i's, where f i's form a complete set of orthonormal eigenfunctions, and a n at the corresponding eigenvalue, where we also know that the eigenvalues of Hermitian operator are real. So, a n is real and f n is one of these eigenfunctions from this complete set of orthonormal eigenfunction. So, suppose psi, the state of the system, is described by f n, which is actually one eigenfunction of the operator A. In that case, what would be the average value or the expectation value of operator A? We simply have to evaluate this integral. We see that since the state of the system is f n, so I write f n star here, the operator A, the function f n, and then I evaluate this integral over all available space. Now, when I see here operator A acts on f n, I know that f n is an eigenfunction. So, therefore, the result of this operation is simply a n f n d tau. A n is eigenvalue, which is a constant. I can bring it out of the integration, and when I look at this quantity, so here this is f n star multiplied by f n, and I am integrating over all the space. So, I know f n is an eigenfunction of operator A. So, it must be a well behaved function, and if it is a well behaved function, I can always normalize it, and if it is a normalized function, so therefore, the value of this is 1 and I am left with a n. So, what does this exercise tell me? This tells me that if the state of the system is defined by a single eigenfunction, by an eigenfunction of this operator, then the average value of this operation of this operator is a n and only a n. And what is a n? A n is actually the eigenvalue corresponding to the eigenfunction f n. We will compare this result with another case where psi is actually not any eigenfunction f n, psi is any other arbitrary function. But we know that if we have another any arbitrary function psi, we can always express it as a linear combination of the complete set of eigenfunctions f I, because f i's are eigenfunctions of a Hermitian operator A, and this set of eigenfunctions, they form a complete set of orthonormal eigenfunctions. So, therefore, psi if it is not equal to any one of these eigenfunction, I can always express it as a linear combination of where C I are the coefficients in this linear combination and F I are individual eigenfunctions of operator A. So, when this holds good, let us evaluate the expectation value of operator A. So, you see I would put now the place here is psi star. So, psi is given as this linear combination of f i's. So, I am expressing it as a sum and I am using a different index here C k star f k star, because this is the place for the complex conjugate. Then I put the operator A and then I put psi. And then I integrate it. When I see here, I see that I have to do an integration, but in this integral I see that there are two summation signs, one over k, another over I. So, when I expand it, you would see that I have many f k, k would go from 1 to as many. So, I would have f 1 plus f 2 plus f 3 all complex conjugate, and in the right hand side I will have f 1 plus f 2 plus f 3 each multiplied by some coefficient. So, therefore, I have many terms. I can rewrite this by bringing these summation signs and the coefficients outside of the integration C k star C I, and then I am left with f k star A f I d tau. So, I brought C k star and C I outside. I kept f k star, which is an eigenfunction of operator A, f I which also is an eigenfunction of operator A inside this integration, because these are the functions that the operator can act on and then they will have dependence on this variable. So, I have to keep them within the integration, and since C k and C I they are mere coefficients. So, I can bring them out of the integrations because they are anyway going to be constants. When I look at this term over here, I see that A operator A, when it acts on function f I, since f I is also an eigenvalue, I am sorry, f I is an eigenfunction of operator A, its outcome of operator A's action on f I is going to be eigenvalue, which is A I multiplied by f I. So, therefore, C k star C I, and then when I apply A on f I, I get A I, which is again a constant. So, therefore, I am bringing it out because this is an eigenvalue, and I am left with f k star f I d tau. This integral we already have seen. What is this? This is an overlap integral between two eigenfunctions f I and f k. We know that f I and f k are two eigenfunctions of a Hermitian operator A. So, they are orthonormal. So, that means I can replace this with a Kronecker delta function. I continue my discussion here. So, I have k I C k star C I A I delta I k. If you remember this Kronecker delta, when I is equal to k, the value is 1. If for all other possibilities, when I is not equal to k, this is 0. So, therefore, when I have two sums, let us say I expand the sum over k. So, I see only one value of k will survive. Only when k is equal to I, then delta I will become 1. For all other values of k, delta I k will become 0. So, therefore, the net effect of this summation over k is simply that this only one term will survive, and that term will be when I equals k, and when I equals k, this value will become 1. So, therefore, I can simplify it further by telling it all the summation they will only survive only when k is I. So, I have C I star, C I, A I, or further simplify it as C I square A I. So, this is my expectation value or the average value of measurement of A when the state function is not an eigenfunction of the operator A. If the state function is an eigenfunction of operator A, I get the outcome of this experiment as only one eigenvalue, and that is A n. But when the state function is not an eigenfunction of operator A, I make measurements on many identically prepared system, and each time I will get some values, but it is not any arbitrary value. The outcomes of this experiment are still AIs, the eigenvalues of this operator A, because remember postulate 3 said that when you make a measurement, only allowed observables are the eigenvalues and nothing but the eigenvalues of that operator A. So, operator A's eigenvalues are AI. So, therefore, even when the system is not an eigenfunction of that operator and I make measurement of corresponding to that operator, I am still going to get eigenvalues as the outcome of this experiment. But now there is something else over here. The Ci square actually provides me an idea about what is the probability of observing this AI when I carry out this experiment. So, that means when the state function is an eigenfunction, I have only one possible outcome, and that is the eigenvalue. When the state function is not an eigenfunction, I do the measurement, I will still get the eigenvalues, but in different distribution. Some 30% of the time I get eigenvalue 1, 20% of the time I get eigenvalue 2, 20% of time I get eigenvalue 3, so on and so forth. So, this Ci square actually gives me the probability of observing an eigenvalue as an outcome of this experiment. So, this is a very critical difference between what I get when the state function is an eigenfunction or when the state function is not an eigenfunction. Here from this discussion you see therefore, the Ci's are important quantities, and we will now discuss how we can get these Ci's. Remember we defined our wave function psi as a linear combination of Ci f I. So, the wave function, the state function is expressed as a linear combination of the eigenfunctions which form a complete set. So, I want to know about what is this Ci. So, to get that I carry out the following evaluation. I evaluate the overlap integral of f k star. F k is another eigenfunction, is one of these eigenfunction from the complete set of orthonormal eigenfunctions of operator A. I want to evaluate this particular integral, this particular overlap integral. So, when I do this, you see f k star and psi is I am expressing now as the, I will expand it now Ci f I. So, I see this. So, you know I can bring this summation sign outside, and this is the overlap integral between of two eigenfunctions of the same operator, same Hermitian operator. So, therefore, they are going to be orthonormal. So, I am replacing them this integral as a Kronecker delta. I know when I equals k, Kronecker delta value is 1, when I is not equal to k, this value is 0. So, therefore, even if I have a summation over here, only one term will survive, and that term will be when I is equal to k, and in that case I will have only C k. So, in the summation term, only one term would survive when I is equal to k. So, in that case delta k k becomes 1, and then I am left with this coefficient C k. So, I actually have some idea about this C k, which is actually the coefficient of coefficient in this linear combination that I am expressing the wave function with, and C k is the coefficient corresponding to the eigenfunction f k. Now, I I got some idea about this Ck. What does this tell me? This tells me that when I do a linear when I have an arbitrary function psi and I express it as a linear combination of the eigenfunctions of from a complete set of orthonormal functions, in that case the coefficients corresponding to an eigenfunction is simply the overlap of this arbitrary function with that particular eigenfunction. So, this overlap integral gives me an idea about this coefficient Ck. We would do one more thing to get some more idea about this coefficient Ck. We know that this psi, the state function, is a well behaved function. So, therefore, I can always normalize. Suppose if psi is a normalized state function, then I can write this expression because psi is normalized. Now, what I would do is that I would expand this psi as a linear combination. So, psi star, you would notice that when I have two expansions to carry out, I am choosing two different indices for this expansion. That is just to make this derivation very general, because if I keep both the indices same I, then I will lose out many other terms. So, this is important to remember. When I have more than two expansions to carry out, I should choose two different indices, so that even when I and k are not equal, then also I can have those terms in my expression. So, again I bring out the two summation signs k I also bring out Ck star Ci and keep excuse me, there has to be a complex conjugate here, because this is psi star. So, I have f k star f I d tau, and we already have seen this quantity a few times. So, you know this is simply Kronecker delta. And the Kronecker delta will survive only for one term, and that is when I is equal to k, and then you would see that this term is simply this. And what is the right hand side? The right hand side is 1. So, I can write this as a general rule, that if my wave function is normalized, then the sum of the square of this coefficient is 1. So, now I have got complete information about this expressing an arbitrary function as a linear combination of eigenfunctions of a complete set of orthonormal eigenfunctions. What is it? That when I carry out this linear when I express this arbitrary function as a linear combination of these eigenfunctions, the coefficient Ci's are simply the overlap integral of the arbitrary function with the eigenfunction, and the sum of the square of these coefficients are going to be 1. Now, we would use the information that we discussed in today's class in one example. Suppose we have this example as here, we have f n's are eigenfunctions of operator A with eigenvalues a n, where n goes from 1 to and so on and so forth. So, it suggests that f i's, so f 1, f 2, f 3, so they form a complete set of eigenfunctions here. And my state function psi is expressed as a linear combination of only 3 of these functions, and the others have coefficients 0. This means, in that case, what will be the outcome if I do the measurement corresponding to the observable A? So, I already know that the expectation value of corresponding to operator A is simply given as psi star A psi t tau. Since the wave function is not an eigenfunction of this operator A, so therefore, what I am going to get is that the linear C I square A I as the outcome. What is C I star square? C I star square is the square of this coefficient. So, here the wave function is written as C 1 f 1 plus C 2 f 2 plus C 3 f 3. What is C 1? C 1 is 1 by 2, C 2 is 3 by 8 square root, C 3 is 3 I by 8 under square root. So, what would be C 1 square? This is 1 by 4. What would be C 2 square? Absolute 3 by 8, C 3 square, that is also going to be 3 by 8. Remember, this is there is I, so I have to take C I star C I, so the complex conjugate. So, that would have 3 by 8. So, what is the outcome of this experiment? This tells that I have 1 by 4. So, that means the C 1 square is 1 by 4. So, that means I would get 25% of the time A 1, which is the eigenvalue corresponding to a function eigenfunction f 1, 3 by 8, which roughly comes out to be 37 and which is 37.5%, and again 37.5% I will observe C 2, I am sorry 37.5% I will observe A 2, 37.5% of the times I would observe the eigenvalue A 3. So, C 2 square, C 3 square and C 1 square, they give me an idea about what is the probability of finding an eigenvalue A 1, A 2, A 3 and so on. So, this exercise, this example tells us what to expect when we do a measurement corresponding to an operator A when the state of the system is not an eigenfunction. Just to remind you, when I do this measurement, the only allowed observables out of these experiments are going to be the eigenvalues. Nothing other than the eigenvalues are can be observed, but the fourth postulate told us that what should we expect, what proportion in how many times, in what percentage we would expect which eigenvalue. This is what the fourth postulate told us. We will continue our discussion in future classes. Thank you for your attention.